Okay, so in this section or segment, we're going to study bound currents and their relationship to free currents. And we're going to compare this to our development of bound charges and free charges in electrostatics. Okay, so you'll remember in electrostatics, we started off with our divergence equation for E, and we rewrote the bound charge in terms of the polarization. Okay, so if we take this equation here and we substitute for divergence of E in here, then we generate the following relationship. Okay, so what we know is that in electrostatics, the bound charge is linearly related to the free charge and it's opposite in sign. And that all made sense to us. If I put a positive free charge inside a dielectric, then it will attract the negative end of the dipole moments, if you like, towards that positive charge. So the bound charge is always going to be opposite in sign. If this constant of proportionality goes to zero, then there is no bound charge, and that makes perfect sense. From this relationship, we derived Gauss's law, an effective Gauss's law for our vector D. Okay, so this was how we went about studying bound charges and free charges in electrostatics. Well, in magnetostatics, the situation is really very similar. Of course, we're not interested in bound and free charges anymore. We're interested in bound surface currents and free surface currents, and our starting point is the curl equation for B. Okay, and of course B responds to all the currents, both the bound currents and the free currents, and B makes no distinction between them. We make a distinction because it's useful. We then introduce the relationship between the magnetization and the H field. Okay, so what we have now is we have a relationship between the curl of B and the bound volume current density. All right, very much in the same spirit as developing an equation which relates the bound volume charge to the divergence of E. Just as we took this equation and we substituted in here to get an equation in terms of rho bound, we're going to replace the curl of B in this top equation by this expression in terms of JB. You'll see that the mu naughts are going to cancel and we're going to get an equation which relates J bound to J free. Okay, so that is the relationship that you'll generate if you do that one line of mathematics. And now we can write down well, now we could either use in studying magnetic materials either our Ampere's law for H or our Ampere's law for B to solve problems in the presence of magnetic materials. That's what we're going to do now. I'm going to study an example, a very straightforward example, and that example I'm going to highlight how you would use Ampere's law for H to calculate all relevant quantities and how you would use Ampere's law for B. The problem we're going to study is the following. Okay, so what we've got here is a current carrying wire carrying current I, and it's embedded inside a solid cylinder. This is a solid cylinder of magnetic material, where the magnetization is going to be related to the H field by this constant here. I always forget the name of this constant, so I'm just going to call it chi. All right. So if we were to use Ampere's law for H, we would wind up with the following expression for the H field inside the magnetic material. Actually valid everywhere, but in this case we're going to be interested in it inside. Alright, so the integral of H dot dl, this is Ampere's law, is I. Now I here is I free. Alright, this is the free current. It is the current that we are injecting through this wire. The bound currents are going to be the currents due to the any magnetization or curl of the magnetization in the volume, or M cross N hat at the surface. Okay. Once we've got the expression for H, we can, from symmetry, we know that the field is going to be in the phi hat direction. It's going to be like this, and the integral of H dot dl becomes very straightforward. If I put a little Amperian loop in here of radius r, this is radius r of this loop, then I would get okay, so there's our first result, our first expression. Once I have this expression, of course, I can generate expressions for M, and I can generate an expression for B. So let's do that. They're very straightforward. And if I wanted the expression for B, I would probably use the following relationship. Okay, and so there are all the relevant quantities in linear magnetostatics that I might be interested in calculating for this problem. It's a very straightforward problem, but straightforward problems like this are useful to illustrate how you use tools and the conceptual ideas behind the problems. What we're going to do now is rather than using the Ampere's law for H, we're going to use Ampere's law for B, and of course on the right hand side all currents, both bound and free currents, are going to appear. So studying the same problem, if we wrote down Ampere's law for B, we would have the following expression. Okay, so this would be our starting point, and explicitly we've had to include both the free current, which in this case I'm calling I, this is the current flowing in the wire, and all bound currents, which are IB. But we have a relationship between IB and I. We derived that on the previous page. And there is our expression for B. And you'll see that this does indeed agree with the equation that we derived on the previous page. And now, of course, given the linear relationships we have between B and M and H, we could generate from this equation for B the other two expressions that we derived using Ampere's law for H. And of course, we'd get the same answers. We would get that H is the following. And M and once again we would have generated all the expressions of interest for this problem in linear magnetostatics. Now the point that I want to emphasize here is that the H field is not necessary. It's often very convenient, it's often very useful. It responds only to the free currents, but as you've seen in this particular example, we can do everything just by considering the magnetic field alone. All right, so you can either use H or you can use B. In many situations, H is the more convenient field to use.